quantum mechanics in the way that is necessary for quantum computing. So, quantum mechanics in a fashion that is useful in computing. Okay. So, what we will do is we will be making our quantum mechanics be a linear set of equations. Okay. So, the way you have learned quantum mechanics earlier, that might be slightly different from the way we will be approaching quantum mechanics now, although the principles and everything else will remain the same. For the benefit of utilizing this in terms of computing, we will set it up in a way so that it can have a set of linear equations that can be solved, and that is the approach that we will do right now in terms of quantum mechanics. So, what are the main aspects of quantum mechanics? One of the main aspect is that it is going to be probabilistic. Next is it will have an equation of motion which is different from the classical one, and the equation of motion here is the Schrodinger equation. Okay. Now, there is the equation motion, the Schrodinger equation can also be expressed in terms of Heisenberg, known as the Liouville equation, or when you have a set of quantum systems, then it is more. Okay. So, each of these expressions essentially are going to give rise to the quantum mechanical solutions which are of use to us. So, when we start with Schrodinger equation, as we have done before, or the Heisenberg form, they are essentially one and the same, and the Liouville equation is the form which is using more than one system. Okay. Schrodinger equation and Heisenberg form are essentially for one quantum system, whereas when you have an ensemble or a set of quantum systems, then you will be using the Liouville equation. Now, for all practical purposes, when we look at quantum computing, Liouville equation becomes most important, because we are actually trying to see how an entire set of problems are being solved simultaneously, and the Liouville equation is the one where you have all the processes working together. So, it is an ensemble solution. So, in some sense, this is the one which takes into account additionally the effect of statistical mechanics. So, right now is the right time to tell you about this, because you have seen both quantum mechanics and statistical mechanics before, and we are just combining them to get our final expression, which is the Liouville expression, which is an ensemble approach of dynamics. Okay. So, when a set moves, what is going on with it? So, there are a few things which we need to do here. One is to use the Pauli representation. So, the Pauli representation is something which actually uses matrices which can be equated to vectors, and these help you in picturizing what you are doing in quantum mechanics, right. So, a two-level system, for instance, which can be as simple as spinning one way versus the spinning other way, or two states of a system, say ground state or an excited state. These can be represented in terms of both matrices and vectors, and the convention used is going one way or going the other way. So, this is known as the bra and this is known as the ket. In total, it closes and becomes a complete set. So, this is the representation which goes, which gives a overall idea. There is, see, technically there is no pictorial understanding of this, but it helps you in understanding the math a lot more if you take this approach. So, that is what we are going to do. We are going to use the bracket principle, okay, and put it in a way so that all the mathematics that we write gets short form. Okay. So, that is where we start off. So, it can be as simple as a spin system or it can be states that we are looking at. So, that is how we represent the quantum mechanical systems from where we start. So, the first principle that we want to look at is to see how we can represent this. So, whenever you want to represent a vector, we are used to our three-dimensional picture, which will essentially have a sphere, and in this sphere the vector can be either in one of the directions or it could be in the other direction, or so you have to choose which one where it is. Either it is on one dimension, if I choose to call it z, then I have the x and y in these directions, say y and x. It depends on the convention you choose how it is going to look like, but the vector can essentially rotate in this frame, right. So, this is simply a sphere in which we can assume a vector to have different directions. Based on this simple principle, you can define how your quantum system is going to be. So, technically whenever you are measuring one of the different conditions of a quantum system, the measurement is in one of the directions. So, either you are measuring along the z x plane or z y plane, or if you would like you can measure along the x y plane. Typically that is not what it is, because our convention is that we will be having our z axis along the direction where the vector is going to align for us. This is a vector which is quantum vector for you, right. So, what we are doing is we are saying that this is the representative vector based on which we can have this. So, if it actually goes completely the other direction, then we call that this is a flip. So, essentially it has gone from one state to the other state. So, it can be through this in between step, or it can just shrink. So, the observation when you make, you will essentially see the observation will be that the upper one, the arrow in the upper direction is shrinking, whereas this is growing, or vice versa. This is growing and this is shrinking. This is shrinking and this is growing. So, this is how it is related, either this is shrinking and this is growing, but in the middle there is always this other state where the system can be present while this shrinking and growing is going on. which means that there is this other plane, xy plane. If I do not measure that, that is the plane where the quantum vector, if we look at it that way, can reside infinite in infinite possibilities. And that is one of the biggest advantages of looking at how the quantum system evolves. So, I am making an analogy to a classical system. In a classical system, you have vectors, you have pictures that you can draw. So, I am trying to make that analogy, right. So, we all know for sure that there is no way of representing a quantum system in this particular way that I am trying to do right now, but it turns out that they have a very strong correlation, at least in understanding. The picture is that when we measure, we only measure it in one way or the other, and that particular act, which we call as measure, is essentially the act of finding the projection in a particular plane. So, as long as I define my principles in a way that we are able to understand what we are saying, there is no problem. So, if we can define that a projection is a measure of my quantum system in the plane which is my observable plane, so projection into observable plane. So, projection into observable plane is my measurement. Once I do that, then I will see, for instance, in this particular case, that either the vector is shrinking in one direction or growing in that direction, and correspondingly in the opposite direction it is becoming the opposite. So, if it is simple two state system, which essentially makes sense that my process where I am having a motion from, let us say, the ground state to, let us say, the excited state, if I am measuring the excited state quantity, it is going to increase when I push the system going towards the excited state, and correspondingly the ground state will go down. So, if I make a simple measure of how, let us say, then my total probability is always 1, I will always have a picture which will look like, I do not know how you define things, but let us say in terms of time I have a change which can be as simple as a simple linear change, one going down and the other correspondingly going up. Okay. So, there will be a point of time when everything will be 50-50. Right here is where half and half of each of the two states are available. So, this has gone down by 50%, this has grown up by 50%. Okay. At no point of time, therefore, is any loss or any kind of event. But this is relying on the fact that we are making measurements all the time. If I make only one measurement and do not make the other measurement, then there is always this possibility that while this is going to the other side, there is a chance that it can also be in the in between case. And this is the power which is very different from a classical system, because in a classical system it will always be what I just showed you. Whenever something disappears, it always appears on the other side. Here, since there is no line of action that you can draw from one state to the other, you can only make a measurement and comment, which is basically a projection. Whenever you make the measurements, which is a projection, you will have this story exactly as I mentioned, which is the classical answer. But unless and until you complete the measurements, all the other possibilities exist, which means that at any point of time nothing may be on the upper side or the lower side, they are all actually precessing at the very middle. Okay. And if you measure at that point of time,
so is it represented as 0.5 probability?
No, the point is when it is precessing in the middle, it can go either way. Whenever you make a measurement, either it will be possibly going into the y dimension, I mean plus z dimension, or the minus z dimension, if it is exactly sitting in the middle. If it is precessing exactly in the middle, then the probability of it going one way or the other is 50-50. So, either you will see 50% going one way, 50% going another way, and since you are never making one measurement, you are making a large number of measurements, you will get a probability which will give you a 50-50 split of the two. So, which will confirm exactly with your classical answer, and that is the beauty of it. So, which means that I can now say that my quantum system will give me the classical answers whenever I make a measurement. So, this point is extremely important, because otherwise you cannot have anything known as computing with a quantum system. Okay. The fact that whenever you make a measure, you will always get the solution which is guaranteed classically, you will be able to use this as a computing device, otherwise it is not possible. Okay, because we had gone through a few of the initial preliminary discussions where we had said that there was this presumption that what is the point of a quantum computer, it will never work because it is always probabilistic, there is no answer which is going to be correct, because every time you will get a random answer, so that is not the point. But here it is not really random, you will always get what you are supposed to get classically also. It is just that until you make the measurement, all the other possibilities exist, and that is the thing which you can take advantage of. If you can take advantage of that, then quantum computing is useful, otherwise it is just like a classical computer. Okay, so that is the basic point here which we would like to stress. Okay, so now that we have sort of understood this, let us go over a few of the important points which is in terms of measurements. First thing to understand is uncertainty. Uncertainty. So, whenever you have a measurement in quantum system, it will be associated with uncertainty, and this uncertainty was devised by Heisenberg. This Heisenberg uncertainty principle essentially is just a measure of the deviation that can happen from the average measure. At any point of time you make a measure, the deviation it can have from the most or the average measure is what is known as a Heisenberg measurement uncertainty. So, in other words, so say for example, you are measuring position x, right, position. If you are measuring position, then the associated uncertainty delta x for the position will be given by the fact that you have say an average position minus the position that you measure at any point of time. That is your uncertainty, right. Every time you will not get the right value, which is your average value, but there will be some deviation from that. As long as you can and the point which is important in the uncertainty principle is that there are properties of this uncertainty which can be correlated, and that gives you the advantage or gives you the limits of measurement. This particular deviation, deviation from mean, deviation from mean, but the more used uncertainty parameter is the square deviation from mean, right. So, that is given by, typically at any point of time, if you want to write what this average value means, it means this is my measure. So, this is my parameter that we, so position we want to measure associated with a wave function which is my psi, and with respect to the wave function I get the average value of position as x. right. Now, this average position can have a deviation which is mostly done in this form squared to say I have x minus so this is the square deviation. Okay. So, this particular deviation is the square deviation or the variance, and what you are more used to is the root mean square deviation, which is basically the square root of this. So, this is your root mean square deviation. So, whenever you make a measure, so if I want, I can replace this x, which is position in my case, to any measurement value or parameter which can be m representing any measurement. Okay. So, this measurement can be position as I just showed you x, it can be momentum, it can be energy, anything that you want to measure. Now, some of these measurements are not possible to be done simultaneously. Now, this is coming from quantum mechanics. This is the part which you have already learned, but we have to revise here because this is the part which is very critical in terms of the quantum picture. In the classical picture, there is no reason to expect that there will be any complementarity amongst measurements. So, I have arbitrary precision of measuring say position, velocity, momentum, all the measurements that we want to. However, in quantum mechanics this is not true. We have to have only a few parameters which are allowed. Now, this is coming because, as I have been telling, the character of quantum mechanics says that we are not going to have the path laid out for us. We can only measure one point and we can make the measurement at the other point. We cannot actually have a continuous evolving measurement possible, because every time you make a measure, it is a classical unit. Okay. So, basically the definition of measure is that I am converting all my quantum aspects into classical analogues. They need not be the same thing. Okay. A classical analog is not classical, it essentially means it has a correspondence to a classical principle, that is all. Okay. So, measurement in quantum mechanics has a classical analog in terms of saying that I am able to say that every time I make a measurement, I am actually able to correlate to my classical concepts. So, that is the whole idea here. So, what are we going to do about this? We are going to see how we can use these principles to go further. So, the first principle we introduced here was the fact that quantum mechanics can be represented by vectors, okay, which can be visualized. Okay. So, that is the first concept which we said. Second concept we said that every time you make a measure, okay, you are making a measurement implies correspondence to,
So visualize means measurable.
no, visualize means you can picturize, or maybe I should use the word picturize or picturize. See, otherwise quantum mechanics has no way of understanding how it is, right? I mean, quantum mechanics is supposed to be only a math. You are not able to say, for instance, understand how the quantum mechanics parameters are going to be one way or the other, because wave function, for instance, there is no physical analogy of wave function. I cannot feel a wave function. I cannot have any aspect of wave function. However, if I can somehow have certain kinds of wave functions come together, they will end up producing results which is measurable, right. So, that is that certain kind that we are defining. We are saying that these wave functions are nothing but ways of representing vectors. That is another way, right. So, I have, so actually in the exact Dirac picture, so this what we are trying to build up is a Dirac picture. So, let me actually tell you the exact way Dirac picturized it. In the Dirac picture, the wave function psi is consisting of, as with everybody, with say many coefficients I, j, let us say, well, okay, fine. It can continue. Okay, it is a superposition of many different wave functions, right. That is my wave function psi, final wave function, but it has many other wave functions. Now, the idea was that no matter how it happens, the wave function, we looked at it when we were doing it earlier also, the wave function, so this is the wave function, was supposed to be normalized, which means that no matter what happens, if you take the square of the wave function, which is something which you consider as the probability function, that is having a maximum value of 1, because that is what a probability does. Okay. So, wave function has no meaning, but the probability function, which is the square of the wave function, has a meaning, and therefore, it can have values ranging from 0 to 1. Okay. So, the Dirac picture essentially takes this and puts it in a different perspective, saying that in that case, this wave function, if you want to look at it that way, should have a connection to how all these parameters add up to give rise to the final answer. So, this particular wave function can be connected to the total observable issue, which is composed of many different components. So, at any point of time, if I actually align it such that only one of the aspects are going to be there, then it becomes a pure function. So, in other words, if I can have ai and say a star I come together so that that becomes 1, then everything else a I, a j, they all should vanish. This is what happens. So, I am in other words, I have actually taken a projection along my psi direction, my phi I direction. That is my projection. Okay. So, this is basically the Dirac picture when I am actually taking any state and picturizing it in this manner. So, I can take the extreme of saying that this entire vector picture, this entire wave function picture can be accommodated in the vector mode, where I am picturizing this, and then I am deciding how I am going to take the projection along which dimension. And that is why the sphere picture only works for just the beginning understanding. A real quantum system has something called a Hilbert space, where the space can be infinite, right. All the possible numbers of wave functions can be there. So, it can be infinite set. So, for us to visualize again becomes completely impossible because we do not know anything more than 3 dimensions. If you tell me anything better than a sphere, I do not know. Higher dimension sphere, I have no idea, right. But the Hilbert space is an extension of this idea into a mathematical world. So, we are just connecting the mathematical world to an understanding which we can understand. So, we are saying that to a picture which we can understand. So, we are saying that we are actually taking an n dimensional space to a space which is understandable to us. So, this Hilbert space of n dimensions is being brought down to a 3D space which is my vector representation just for understanding. But it turns out that this Dirac principle of doing the whole picture.
But sir, for Hilbert space there is n dimension, and we are cutting other n minus 3D dimension to get 3D dimension picture. For it.
No, we are not cutting anything. We are just saying that there can be n dimensions, but whenever I am interested in understanding how the picture is evolving, I am only able to draw it in 3 dimensions, right. That is the only way I can represent. I cannot understand anything more than that. That is all. Now, it is up to you if you want to simplify. We are not doing anything. So, all I am saying is that at any point of time, whenever I take a slice or a projection, it is not in any of the n dimensions, it is only in 1 dimension, which is my measure, because the lab frame ultimately is corresponding to only the 3D. Okay, so that is the idea. So, we are always collapsing. So, the key word here is collapse. So, this idea of collapse is the fine idea of the measure. So, measurement corresponds to collapse. Okay. So, you will be hearing this term too many times in quantum computing, and that is why, or quantum information, that is why it is important to know it right off at the very beginning. What is the principle of collapse? The collapse is nothing that you are just going to take this entire n dimensional object into a observable regime, observable frame. So, we are just creating an observable frame. So, our observable frame of reference is letting us collapse the system for a measurable quantity. Now, in this regard, we have also already introduced you to the idea of uncertainty, where we had said that every measure has some level of or some bit of deviation from the mean value. If you take the square of that, what you will find is that it is the actually difference of the square of the means with respect to the so, basically it is a mean square deviation, because you are taking the average of the squares minus the mean square to get to your squared deviation value. So, based on that you can actually construct something as your uncertainty. And the beauty of the quantum system is that there are measurements which cannot be made more accurate than a certain quantity, and that was given by Heisenberg, which basically states that if you take complementary measures, say position and momentum along that same direction, then you cannot have each of them being measured with arbitrary precision. There is a limit to the maximum value that you can do that. It's often represented by h square by 2 or h cross square. Right. So, this is uncertainty. You can actually derive this. So, I will leave this as an exercise, how to derive this based on this simple derive based on the simple definition. Okay, so I leave this part as an exercise to show that this momentum and thing can be done, because you have been exposed to the, so x is position, which means that the operator. So, in order to derive that, you need to go back to your term of operators. So, the x, which is position, is an operator which is x, and in terms of operators we always put a small kappa on top of it. This is just for your, so this is my measure and this is generated by my operator, which is, in this case, this is position. Similarly, there is momentum Px. Now, this can be generated by an operator which can be simply written as Px, this thing, but it has a meaning to it, and we will have to know how that, what does that correspond to, right. Now, you might remember it from your earlier studies that this is nothing but d by dx m d by dx, right. But how did you get it, and why did you use the minus sign? There is a little bit of a history to it. Right now, if you use either plus or minus, you will get the same answer for almost everything, but there is a reason why the sign minus was chosen by, again these are all, this operator math was given by Dirac. This entire operator math for doing quantum mechanics was derived by Dirac, and the reason of this entire math was required because he is the one, if you remember, who introduced or who was able to solve the entire go beyond the Schrodinger equations to be able to show that spin quantum number can also appear as a solution rather than being ad hoc put in as was done before him by Pauli and others. So, the exclusion principles and all of those principles are very nice, but mathematically how do you arrive at it was given by Dirac based on all these principles, and he had to use the idea of operator math to get this to work. Principally, this is a very shorthand method. So, this is shorthand method in comparison to differentiation, let us say. Comparison to differentiation and integration. And this particular operator math makes everything into a linear algebra. So, this operator math also serves the purpose, transforms quantum mechanics into a set of linear equations. Okay. So, the differential equations or the equations which look more complex are converted into a set of linear equations thanks to the operator math that is being introduced by this approach. So, for this particular purpose of quantum computing, we will definitely be using operator math, because that is the way we can go ahead and do this. Some of you might have been exposed to this earlier, operator math, because the eigenvalue eigenfunction equation that you have used before is nothing but an operator math kind of an equation, right. It is a shorthand notation equation, and it is very simple because it actually takes this entire approach and solves the equation simultaneously. Now, whenever you talk about set of simultaneous linear equations, what is the next thing that you need? Matrices. whenever you need to solve sets of linear equations, you need simultaneous linear equation, you need matrices. Okay. A little bit of linear equations. First thing first, how will you represent your vector as a matrix? So, for the simplest vector, which is only 2 levels, which represents only 2 states, it can be a, these are my 2 vectors. This represents vector going, let us say, up, down, or vice versa. It is up to you how you choose it, but that is how it is. So, vectors can be immediately represented by this. If you have a 3D vector, then instead of this, it will become 0 0 1 or 1 0 0, right. So, similarly you can choose, and one of the things which you can immediately see is that we are choosing only one. So, this is already proving that I am going to consider projections. So, these are my 3 different cases, 1, 2 and 3. Okay. So, correspondingly, whenever I have chosen the vectors, my operators will have the same kind of matrix forms. So, whenever I deal with a vector which is only going to be 2 by 2, I will have a corresponding operator which will be, so this is a, if I have a 1 by 2 vector or a 2 by 1 vector, then I need a 2 by 2 operator. Similarly, if I have a 3 by 1 or 1 by 3 vector, then my operators are going to be 3 by 3, and so on and so forth. So, in principle you can have n by 1 or 1 by n vectors, okay, and correspondingly I can have n by n operator dimension. So, this is my dimension. Okay. So, this is how you set it up. So, this kind of gives you the idea of where we are leading to. The simplest one that you know is the Schrodinger equation H psi equal to E psi, and if we are allowed to replace them, by the way we have done it here, for the simplest case we will be having a 2 by 2 matrix giving rise to, say, this, and the corresponding matrix looking like this. Now, generally you know that this particular matrix is supposed to be Hermitian. So, what will happen is H 1 2 is going to be H 2 1. So, that is the way the very first equations that you are used to comes back to you as linear algebra and maths in terms of matrices, and that is how your computer gets set up in one way or the other. So, I am actually now taking you from your physics knowledge of quantum mechanics into a mathematical set which will give you a computational way of looking at it. Okay, so, this is the first step of trying to understand how we go about computing from a point which is pure physics on one end and looks completely incomprehensible in many ways, to a place where you can relate it to the simplest possibilities of a classical computer. Okay. Now, it is easy to start with the 2 conditions, 2 by 2 conditions, because that is directly corresponding to your bit parameters, because in computers also you are always going to do bits and operations relating to bits. So, let us just look at a couple of very simple examples. Let us look at one simple case where we can connect computation to this kind of an operation. Say you want to have the vector state of 0 1, which is of one direction, go into the 1 0 state. It is going from, so it is a 2-dimensional case. So, this is my vector upwards. So, it can be x and y. I am going from plus x to minus x. All right. So, this is my minus x. So, when I go from between these two different cases, what is it that is going to look like for my case? So, what do I have to do to get this happen? So, the idea is to find out a way how I can have 0 1 become 1 0. What will you do? What do you have to multiply this to give rise to this? So, this is my operator and this is my vector which I am using, and this is my resulting answer. So, this is my essentially this is my answer. So, whenever I finally look at the state of the vector, I will be looking at this is my answer, this is what my initial condition was. So, this is my initial, this is final. If I want to make this happen, what is it that I have to do? What kind of an operator do I need? 2 cross 2 is fine. What are the elements? So, this particular operator that you will discover right now is something which is a NOT gate in terms of a computer, right? I have just inverted. So, whatever was before has become the opposite, right? So, it is a NOT gate. So, in order to look at it in this form, all we have to do is to find out how an operator looks like for this. So, for those of you who have forgotten the rules of matrix multiplications, is this, right? This plus this and the other way, right? So, if you do that, what is it that you will use to get this one?
Second column is 1 0.
1 0.
The first column is arbitrary. Yes, sir. First is 0 0. Anything.
Would that work?
It's actually arbitrary. First column is actually arbitrary. You can take anything.
Would that work? Everything will work. Okay. So, this idea of being able to create results which are computationally useful is one of the first steps in figuring out what is it that you would be requiring for a quantum computer. Okay. So, I wanted to just have you understand where we come from when we are going to proceed in this direction. There are lots of difficulties that you will find, because even for this simplest operation that we wanted to do, it is almost like an inverse operation, right. You have to actually look at what you are trying to get from where you are and what do you have to do in order to get there. This is what you have to keep on trying to get this, but nature does it in a much more simpler way. So, we will have to actually do that in that easier manner, and that is what we will try to do when we are going to develop our quantum computing ideas for doing this. There are many hurdles, and that is one of the reasons why we do not have one yet in reality sitting everywhere, but we have been trying. There are lots of attempts and things which are going on. We are going to stop today here. We will pick it up from the next in this class. Thank you.